Welcome back. This is the solution for number 2 on our optimization worksheet. Problem 2 says find the dimensions of a rectangle with perimeter 100 meters, whose area is as large as possible. This problem is very similar to the example we did in class on Thursday, where we were building a rectangular fence against a stream. This just doesn't have the stream component. Okay, so our first step is usually to draw a picture. In number 1, there was no picture. We just kind of labeled our variables, but this one's talking about a rectangle. So I'm going to draw a rectangle. All right. Find the dimensions of the rectangle. So I'm going to label the rectangle's dimensions. This side would also be X. This side is another Y. So X and Y are all I need. It's telling us the perimeter is 100 meters. And the area we want to be as large as possible. So this comment at the end of the sentence, the area as large as possible, this tells me that area is my objective function. So area is the function that I want to set up a formula for it, and that's whose critical numbers I'm finding and all that. So we want to find maximum area. All right, so according to my picture, area would be X times Y. So I'll say A is XY. And then the perimeter being 100 meters is the constraint. Remember, there's always these two separate kind of formulas implied in the problem. There's the thing that you're either maximizing or minimizing. That's your objective. And then there's this extra constraint where it's, it has to add up to this much, or it has to multiply up to this much. That's what this 100 is. So our constraint is that the perimeter has to be 100. So the perimeter is the fancy word for adding up all 4 side lengths here. So that's X plus Y plus X plus Y, which gives us 2X plus 2Y is that 100. This is the only place where this problem specifically differs from the example we did in class, because so one of these 4 sides was a stream and didn't count here, but otherwise our structure is very much the same. Okay, so much like in number 1, where we solved the constraint for one of the letters and then plugged in for that letter. That's what we're going to do here as well. And again, it's kind of a wash. You can choose to solve this for Y, or you can solve it for X. It's the same amount of work and your answer comes out the same at the end. I like working with X, so I'll solve this with Y for Y so that we can delete the Y here. All right, so I get 2Y is 100 minus 2X. And then divide both sides by 2, I get Y equals 50 minus X. So that's going to be the direct connection between X and Y provided by the constraint. So this is what I'm going to plug in for Y right here. So that area becomes a function of only X. So I have A of X equals X times, and now instead of Y, I'm going to put 50 minus X. Right? Because I'm about to take the derivative of this function, I'm going to save myself some trouble and just distribute this X in so that I can avoid using the product rule. This isn't like a mandatory step, but it does make the derivative part easier. So that's 50X minus X. All right, so now I just want to find the location of the maximum of this function. So I'll find its critical numbers and then choose one of my 3 options for identifying the maximum. All right, so my derivative, now that it's all cleaned up, is very straightforward. I have 50 minus 2X. There are no domain restrictions on this formula, so all I have to do is set it equal to 0 and solve for X. I'll add 2X to both sides, divide both sides by 2, and I have only one critical number, which is 25. So my assumption is that X equals 25 is the location of the answer I want. But of course, I'm not done yet. I have to pick one of our 3 methods to actually confirm that this is our answer. It's possible that when you get a critical number down here, it turns out to be a critical number that isn't a max or min. It's just kind of a fakey point. It's also possible, given the information we have so far, that this is a minimum instead of a maximum. And you don't really notice that until you test it. And that would mean that the whole setup is a little bit flawed, right? So it's always worth checking, even if you only have one critical number. All right, so our 3 options for testing it are the closed interval method, where you make the XY chart, We would have to decide on a reasonable closed domain for X, which is possible here. You might say like from 0 to 100 is reasonable. Or we could do the first derivative test or second derivative. I'm going to default to the first derivative test because it's, to me, I think the smoothest, especially if you only have one number. All right, so first derivative test. I'm once again going to start my number line at 0 because we're talking about a side length here. So it doesn't make sense to consider anything to the left of 0, although because this is the only critical number, we don't have to do that to reach our conclusion. So I'm going to mark 25 as my critical number. A prime was 0 there, so I'm just going to test points in between here using 50 minus 2x, my A prime formula. So a number between 0 and 25, let's say 1. If we plug that in here, we'd have 50 minus 2, that's a positive number. If we plug in a number bigger than 25, let's say 100, we'd have 50 minus 200, that's definitely negative. And I have confirmation that 25 really is the answer that I want. The derivative of area went positive to negative, which means the area function went up and then down. So we have a maximum right here. Okay. So our final step is to just kind of answer exactly the question that was asked. So we want to put units on stuff and make sure we're kind of complete. So this said, find the dimensions that maximize the area. So my answer is going to be full dimensions. So I'm going to go back. This is the X value. So I'm going to go over here and say, all right, when X is 25, Y is 50 minus, and I'm going to plug that 25 in for X here. And I get that Y is also 25. Because this 100 was given in meters, that's my distance measurement here. So we'll have 25 meters by 25 meters. And that's my answer. If this question had been asked, like, what is the maximum possible area with this perimeter, we would still have this 25 by 25 as like what's making that happen, but we would actually compute the area of this square, and that would be our answer instead in square meters. So just slightly change how we end the question.